Suppose I push on a box and it moves horizontally across the floor. Most people would agree that I'm doing work on that box. But take the same box and I push on it vertically to hold it up while it moves horizontally. Am I still doing work? It's scenarios like this where I need to use something called the dot product. If you've ever been confused by the dot product, rest assured you're not alone. I know I was when I first encountered it. Today's video will be making sense of the dot product. The dot product is one way of multiplying vectors together. There is more than one way. The result of a dot product is a single value, a scalar quantity, that's telling us how much two vectors align together. Consider vector b here and vector a. The two vectors are perfectly aligned, and the dot product between these two vectors would be a maximum value that happens to be positive. But if I were to take vector b and rotate it 90 degrees to here, now vector b and a are perpendicular to one another. They are not aligned at all, and the dot product between these two vectors would be 0. If I continue the rotation, making vector b now parallel with a, but pointing in the opposite direction, the dot product would give us a negative quantity. What you can see here is that the dot product depends on the angle, right? A different angle gives us a different dot product. That's telling us that the dot product doesn't just care about the magnitude or size of the vector, but also the direction it points in. Physicists and engineers needed a way to model this behavior mathematically, where I multiply two vectors together and get a positive result if they point in the same direction, a result of 0 when they are perpendicular to one another, and a negative result if they point in opposite directions. We can actually see this out with cosine, right? Cosine of 0 is 1, cosine of 90 is 0, and cosine of 180 is -1. That actually gives us our geometric definition of the dot product, where a dot b, or the dot product of a and b, equals the magnitude of a multiplied by the magnitude of b multiplied by cosine of the angle between the two vectors. This equation, I need to be clear, is not arbitrary. It's designed to measure the directional relationship between those two vectors. Returning to my original question involving boxes, displacement, and force. The definition of work is force dot displacement, the dot product of those two vectors. And if we apply the new geometric definition we've gone over, the magnitude of force multiplied by the magnitude of displacement multiplied by cosine of the angle between both vectors, we can actually see how these two scenarios changes the work done. When force and displacement align perfectly, the angle is 0 and cosine of 0 is 1. That gives us a maximum amount of work done. However, when force is vertical and displacement is horizontal, the angle between is 90 degrees, cosine of 90 is 0, no work is being done, regardless of the magnitude of both vectors. Now, this operation actually shows us why work is the result of the dot product between force and displacement. The geometric form of the dot product is useful when we want to try to picture what the dot product looks like. However, physicists and engineers often work with unit vector notation. As a result, we want to be able to do the dot product when we have this notation. Algebraically, this works out to a dot b, or the dot product of vector a and b, equals their x components multiplied together, added to their y components multiplied together. This operation actually ends up being quite simple, right? ax times bx would be 3 multiplied by -2. That's our x components multiplied together, plus 4 multiplied by 5, my two y components multiplied together. We can do this out. -6 add 20, resulting in 14. Here we can see once again the dot product has given us a single value that is a scalar quantity, measuring the directional relationship between both vectors. One of the major advantages to using the algebraic definition of the dot product is when the vectors are in 3 dimensions. It actually extends quite nicely. We can take the product of the two x components, add the products of the two y components, and then add the product of the two z components. And the method actually ends up being the same. We end up with the product of 3 and -2, 3 multiplied by -2, add the product of the two y components, 4 multiplied by 5, and then add now the z components, or the product of them, 2 multiplied by -3, and just perform these operations. We end up with -6 plus 20 take away 6, resulting in a final dot product between these two vectors of 8. And that seamless extension to 3 dimensions is one of the reasons we like the algebraic definition of the dot product, and we can see one of the strengths of unit vector notation. In today's video, we've seen that the dot product is much more than simply multiplying 2 vectors together. It produces a single scalar quantity that's measuring how closely 2 vectors align. We've also seen 2 ways of performing this operation: geometrically with magnitudes and angles, or algebraically using components. Next time, we're going to see a second way of multiplying vectors together, this time the cross product. Thank you for tuning in. This has been D215 Physics, and I hope you have a wonderful day.